Hey guys, how you doing? It's Coach Scott, and we're going to do Unit 1, our first video, Video A, and it's talking about the origins of all this stuff we call chemistry. Where do these elements come from, right? If you look at the observable universe, we know something, right? The universe is made up of amazing stuff. Now, another name for stuff, and that is a scientific term, by the way, stuff. Another name is matter. So humans, even when we were sitting in caves and tents and we were sitting around a fire or what have you, we were wondering, where does stuff come from, right? We've been curious about what this stuff is that is us, right? So the questions are like, where does matter come from? What is it made from? And then why does it behave the way that it does? And we've been working on those since the beginning of time. So scientists have discovered that all the matter in our universe is made up of 118 different types of chemical elements. Now, only about 90 of these occur naturally. The others are man-made. So, in the beginning, the Genesis, where did all these elements that make the universe come from? Where do they come from? So, if you said the Big Bang, that is the most current model or the theory of where the universe came from. In a certain moment in time, there was an implosion, right? The Big Bang that occurred about 14 billion years ago. That's a long time. So it's believed, or the evidence suggests, that the universe began at a single point. Now, at this one spot, it was 1,000 times smaller than the head of a pin. It was also hotter and more dense than any object we can even imagine today. Okay, and this heat from this object still remains, and we call it cosmic background radiation. We'll talk about this, right? So, this universe began expanding suddenly and rapidly from this single point. Now, every piece of matter, all the stuff in the universe came from this small, dense spot. So let's have a little check. And then I'll read these to you, then let's pause your video, and then you answer it, and let's see if we got our understanding. Right, so scientists believe that the Big Bang happened 14 million years ago, 14 trillion years ago, 14 billion years ago, or within the last 3,000, 6,000 years or so. Or I need some help. So pause your video for just a second, make your answer. Okay, so scientists believe that the Big Bang happened 14 billion years ago. If that's what you said, you read it. If not, rewind the video and listen to the beginning of the video. So, 14 billion years ago, in the flash that was the Big Bang, high energy photons or light particles collided with each other, and these formed oppositely charged particles. Now, when this happened, the oppositely charged matter and the antimatter annihilated each other instantly, converting them back into high energy photons. Right? So, in the first seconds of the universe, for reasons we don't really understand or can't explain, it's estimated that one particle of matter for approximately every 1 billion particles of antimatter were not annihilated. Now, if you could figure out why, well, invite me to your Nobel Prize ceremony and let's share some of the money. Anyway, so in this environment, 3 major particles were formed. One of them was a positively charged particle. The other was a negatively charged particle, and the other one was the neutrally charged particle. So let's take a moment and write these down and see if we know what they are. And you can Google these answers too. That's fine. So what are these positive, negative, and neutral particles called? Then what is the magnitude of their charge? What's the size of their charge? And then what is their mass? What are the masses of these particles? So let's pause a second. Pause. Unpause. All right, here we go. So these three particles are what we call protons, the positive charged items, neutrons, the neutrally charged particles, and then electrons, the negatively charged particles. So the magnitude of their charges, there is plus 1.6 times 10 to the minus 19th coulombs for the protons. Of course, the neutrons are negative. There is no charge. And then for the electrons, it's minus 1.6 times 10 to the minus 19th coulombs. What are their masses? Well, if you Google this or looked at a reference source, you saw that the mass of a proton is 1.67 times 10 to the minus 27th kilograms. The mass of a neutron is about the same, 1.67 times 10 to the minus 27th kilograms. All right, and for an electron, it's much less dense, much less massive, right? It's 9.1 times 10 to the minus 31st kilograms, or it's less massive, about a factor of 4. All right, so that's pretty cool. So, as the universe expanded, the plasma and the radiation filling it grew cooler. So when this universe cooled and the stable atoms could form, they eventually could no longer absorb the thermal radiation, and the universe became transparent, like the night sky, instead of being an opaque fog. The photons that from that time have been propagating ever since, growing fainter and less energetic. So bear with me for a second. We're going to watch a little video about the Big Bang and talk about cosmic background radiation. So 1 second. All right, here we go.
And I'm a professor of physics and astronomy at UCLA, and I work on infrared astronomy and cosmology. Well, the most important information that we get from the cosmic microwave background come from, at the lowest level, its existence. I mean, when I started in cosmology, it was not 100% certain that the Big Bang model was correct. And so, with the prediction of microwave background from the Big Bang and the prediction of no cosmic microwave background from the competing theory, the steady state, that was a very important step in our knowledge. And then the second aspect of the cosmic microwave background that's very important is its spectrum is extremely similar to a black body. And so by being a black body, that means that the universe, relatively smoothly transitioned from being opaque to transparent. And then, we actually see effectively an isothermal cavity when we look at it. So it looks very close to a black body. And then finally, in the last, well, no, not quite finally. Let me make one other step. The fact that we are moving through the universe can be measured very precisely by looking at what's called the dipole anisotropy of the microwave background. So one side of the sky is slightly hotter, about 3 millikelvin hotter, and one side of the sky, the opposite side of the sky, is colder, about 3 millikelvin colder out of the 3 Kelvin. So that means we're moving at approximately 0.1% of the speed of light. And in fact, we now know very precisely what that value is. It's about 370 kilometers per second. So that's our motion, the solar system's motion through the universe. And then the final piece of information that we're getting from the microwave background now, in fact, the Planck satellite just gave us more information along these lines, is the measurement of the statistical pattern of the very small, what we call anisotropies, or little bumps and valleys in the temperature. So in addition to the 3 millikelvin difference, we actually have sort of plus or minus 100 microkelvin difference in the temperature from different spots. And so when you look at these spots and look at their detailed pattern, you can actually see a very prominent feature, which is there's about a 1/2 degree scale, preferred scale, and that's what's caused by the acoustic waves that were set up by the density perturbations early in the history of the universe, and how far they could travel before the universe became transparent. And that's a very strong indicator about the universe. The cosmic microwave background actually has this pattern, a 1/2 degree scale, and that gives you effectively it's a line of position, as you have with celestial navigation. When you do a sextant measurement of one star, you get a line on the map where you are. But you can look at the same pattern. This is the acoustic waves set up in the universe. You see that in the galaxies distribution a lot more locally. We're talking about galaxies that might be 1 billion light years away, but to cosmologists that's local. And these galaxies also show the same wave-like pattern, and you can measure that angle at scale locally and compare it to what you see very early in history of the universe. And that gives you a crossing line of position. And that really tells us, where we are in the universe, how much stuff there is. So it tells us that we have this dark energy, which nobody really understands what it is, but we know what it's doing. It's making the universe accelerate in its expansion.
So, interesting video. A lot of concepts that I don't understand, but what they're really talking about is the cosmic background radiation, which is sort of is evidence that the Big Bang is a pretty good model. So let's check our understanding here really quick. So just like before, we'll pause, write your answer down. Which of these pieces of evidence support the Big Bang Theory? Fossil carbon dating, evolution of life on Earth, cosmic background radiation, our observations of the sun rays, or I need help. So we'll pause and we'll give you a chance to answer. Okay, hopefully you said the cosmic background radiation. That's sort of important. Same thing. Following the Big Bang, the universe did what? Expanded and then rapidly stopped expanding, expanded and has not stopped expanding since, or rapidly expanded and then shrunk back to its original size, or expanded and then began shrinking over time. So we'll pause, give your answer. Hopefully you said B, expanded and has not stopped expanding since. So, in the scheme of time, 3 minutes after the Big Bang, the universe began to cool down from 1 times 10 to the 32nd Celsius to 1 times 10 to the 9th Celsius. That's a rapid cool down. And the protons and neutrons begin to combine. Now, about 300,000 years later, the universe had cooled enough for positively charged protons to attract the negatively charged electrons, and the first atoms were formed. Hydrogen 1, okay? That one proton attracted that one electron. You had deuterium, hydrogen 2, where they have one proton, one neutron, and one electron in orbit around the nucleus. Then hydrogen 3, tritium, where you have one proton, two neutrons, a little heavier, a little more massive, and one electron around. Then helium formed with 2 protons, helium 4, 2 neutrons, 2 electrons. Then lithium formed, 3 protons, 4 neutrons, 3 electrons. And then beryllium 9 with 4 electrons, 5 neutrons, and then of course 4 electrons. Now, during the formation of the universe, only atoms of the lightest elements, hydrogen, helium, lithium, and beryllium, were formed. Now, as the clouds of this cosmic dust and the gases from the Big Bang cooled over time, stars formed. And these then grouped together to form galaxies and stars. So the high pressure and temperature within the stars caused the protons and neutrons to fuse together. Now in smaller stars like our sun, Sol, the temperatures are around 15.5 million degrees C, or 15.5 times 10 to the 6 degrees C at the core, and that's hot enough to make helium from hydrogen only. Right? Now there's other stars out there, and in the core of the hotter, larger stars, hydrogen could fuse to make helium. Then heliums could fuse to make atoms with 4 protons, like beryllium. And helium and beryllium could fuse to make atoms with 6 protons, carbon. And then carbon and helium could fuse and they'd make atoms with 8 protons. We know that as oxygen. And in this matter, elements with up to 12 protons, magnesium, were formed in these stars. Now, the heavier elements, right, like aluminum to iron, they formed in supergiant stars because they're that hot. Now, the most massive elements, from iron to uranium, were created in star explosions called supernova. Okay, and these would form the other elements that were above iron, right? So this is a good little chart, and I'll probably put this in your teams when we get done, just showing where the elements come from. Hydrogen and helium, of course, came from the Big Bang. Lithium, beryllium, and boron, okay? Cosmic rays, they were hot enough to like fuse some of the hydrogen and helium together to form that. Then carbon, nitrogen, oxygen, they could be formed in either small stars or large stars on up till we get into iron, Fe. Then iron would be formed in large stars or in supernova, right? And you can see that as you get bigger, as the elements get more massive, they would form from supernova. Now, the mercurium to lawrencium, those are man-made. They're made in super colliders right now. Okay, so pretty cool. And if you think about it, all the elements from in the universe, they're made from stars. That's pretty cool. So if you think about it, atoms, the building blocks of matter, formed in the intense heat and pressure of the early universe, stellar furnaces and supernova. Everything around us, including us, were once part of a star. So in this course, we're going to explore the nature of this star stuff, matter, and apply the principles of physics to understand atomic structure, chemical properties, and predict chemical behavior. So we're going to watch a little video from Neil deGrasse Tyson, which is pretty neat. And I think you'll like it, and then we'll come back and talk about it. And that's the end of this video in just a second. Here we go.
What is the most astounding fact you can share with us about the universe?
The most astounding fact.
The most astounding fact
Is the knowledge that the atoms that comprise life on Earth, the atoms that make up the human body, are traceable to the crucibles that cooked light elements into heavy elements in their core under extreme temperatures and pressures. These stars, the high mass ones among them, went unstable in their later years. They collapsed and then exploded, scattering their enriched guts across the galaxy. Guts made of carbon, nitrogen, oxygen, and all the fundamental ingredients of life itself. These ingredients become part of gas clouds that condense, collapse, form the next generation of solar systems, stars with orbiting planets. And those planets now have the ingredients for life itself. So that when I look up at the night sky, and I know that, yes, we are part of this universe, we are in this universe, but perhaps more important than both of those facts is that the universe is in us. When I reflect on that fact, I look up. Many people feel small because they're small and the universe is big, but I feel big because my atoms came from those stars. There's a level of connectivity. That's really what you want in life. You want to feel connected. You want to feel relevant. You want to feel like you're a participant in the goings-on of activities and events around you. That's precisely what we are, just by being alive.
So I think that's pretty awesome. If you think about it, the atoms that make up me, the atoms that make up you, come from stars. They were birthed, they were originated from stars. And to me, that's pretty awesome. So that just makes it even more important to think that you are important. You are a star. Every one of you guys, you're young scholars, and you come from stars. Almost like we're spacemen and spacewomen. It's pretty neat. So anyway, guys, that's the beginning of what we're going to be doing for this year, and this is where our stuff comes from. If you get down to it, chemistry is the study of stuff. So look forward. This is Coach Scott saying bye for now. We'll be having Unit 1, Video B here shortly, where we start talking about protons, neutrons, and other neat things like that. So for now, Coach Scott saying bye.